Hello friends, Parker here, and this is ParkerZen. Tonight we're winding down with the iconic voice and cosmic insights of Neil deGrasse Tyson as I help guide you toward a peaceful, restful sleep while we explore the nature of time, the vastness of space, black holes, and the fabric of the universe itself. This video is a sleep-focused remix featuring the calm, reflective voice of Neil deGrasse Tyson, completely reworked to provide a slow, meditative experience with calming audio and visual effects we've created to help you unwind and drift off with ease. So take this time to let go of the day, forget about the world, and let's see which one of us falls asleep first, you or me, while listening to Neil deGrasse Tyson unravel the mysteries of the cosmos and our place within it. Let's begin.
A black hole is a region of space and time where the strength of gravity is so high that light has no path to get out of the object. All paths through space-time curve back in on itself. Normally we think of a hole as a hole in the floor, and you fall through, come out the other side. Except it's a three-dimensional hole. You can fall in any direction. That edge, beyond which there's no return, we call the event horizon. It's a horizon. The universe has a horizon too. It is a distance beyond which no information can reach us because the universe isn't old enough for light from anything beyond that horizon to have gotten here yet. By the way, the more mass is in a black hole, the bigger the black hole becomes. In fact, if you run the math on it, it's linear. So a black hole that's twice as massive will be twice the diameter. 10 times as massive, the event horizon, which is our practical definition, the size of the black hole, will be 10 times as. There's a cool exercise we do in graduate school. You can say, given the mass of the universe, how big would the black hole be that contained this much mass? It's the size of our universe to our horizon. And it's like, wait a minute, could we be one giant black hole? The average density of matter contained within the size of our cosmic horizon matches right on with what you'd get for a black hole this size. That's intriguing. Maybe it's just a coincidence. What would it mean anyway for us to be inside a black hole? How would that work? Well, it turns out if you run the mathematics of Einstein's general theory of relativity into a black hole, it turns out a whole new space-time opens up on the other side. And you look behind you and the entire future history of the universe unfolds relative to your time frame. And so the universe, you came from basically ends, and a whole new universe opens up in front of you. Are we that universe that opened up in front of us? Okay, these are mind-bending questions. Well, there's recent research published that suggests that the contents of our universe has sort of a net rotation to it. Well, that'd be kind of weird. So in this study, it observed several hundred galaxies from the best observing directions you can come up with, which is above and below the plane of our Milky Way. And it noticed a net rotation of spiral galaxies in one direction versus the other. So if you look at spiral galaxies, if half of them sort of rotate like that and the other half rotate the opposite way, then they kind of cancel. But if most of them are rotating in the same sense, in the same direction, then that could hint that there's a net angular momentum of the entire universe. So what did they find? That 2/3 of the spiral galaxies measured rotated in the opposite direction as the Milky Way. So 2/3 is not 100%, but it's certainly more than half. We expect this to just be random. Normally in our lives, we think of something that rotates because some other force set it into motion to do so. And we look in the universe and everything is rotating, and then you ask, what force is making that happen? Turns out, all of our evidence suggests that when you make a galaxy or a star system or a star or a planet, there's some gas cloud that started it. If the gas cloud has any motion at all, the tiniest amount, as it collapses, its rotation will speed up. The gas cloud that was large, moving just a little, will move much faster as it gets smaller. And you know this already when you see ice skaters. When an ice skater spins and they want to spin faster, they start with their arms outstretched, and they have a certain rotation speed by virtue of that. As they bring their arms in, this is a phenomenon of physics called the conservation of angular momentum. If you start out large, slowly rotating, and now you're half the size, you're going to be rotating twice as fast. If you want 1/10 the size, you're going to be rotating 10 times as fast. This is why everything in the universe has some kind of rotation, because it's essentially impossible for any large gas cloud to not have motions within it to begin with. Often they're thermal motions. There's turbulence within the cloud before it sort of collapses to become something solid. Because of the turbulence within the clouds, there's no reason to think they would align with each other. They're each independent entities, so that when they collapse and the final product is spinning, there's no reason to think that the spin of this object is going to match up with the spin of an object over here. We have every reason to presume that there's no net spin direction of the universe or objects within it. So if we find and confirm that there is, we got to go back and ask, how could you get that, given our expectations of randomness? Well, that was linked to the idea that we might be in a black hole. Here's why. There's only two kinds of information you can obtain that are preserved inside that black hole. The mass, the total mass, and the angular momentum. Because anything falling in, if it falls in with a swirl, toilet bowl style, that angular momentum continues into the black hole itself. If there's a net angular momentum of the universe, where did it come from? It's not obvious that would come from a Big Bang, which is an explosion in all directions, statistically evenly. What could it be? Could we be a black hole with a net angular momentum of stuff that spiraled into us? So that's where the black hole connects back to whether the universe is rotating. So I look forward to seeing whether this result is confirmed or falsified. It's an intriguing result. And the number of galaxies was not very large, just a few hundred. And there are billions of galaxies out there. So I'll reserve judgment until I see what others publish on this subject. We saw the centers of galaxies were behaving really weirdly. Stars were moving faster than they should have, given how much gravity was tugging on them. And we said, dude, something's got to be there. And it's got to be really small because we're tracking stars really close to the middle. Well, if it was made of ordinary matter, how big it would have to? It had to be really, really big. So this has to be really, really small in order for this to happen. The only thing we know that could fill that small volume and have that much gravity is a black hole. So it's suspected for a long time. It was confirmed that as a common thing by the Hubble telescope and first photographed by this recent result in the galaxy M87. The very first black hole ever discovered happened like in my day, like when I was in college. I was working in the X-ray group at the Center for Astrophysics. It was a summer job. I was an undergraduate. And the X-ray group had pioneered small portable X-rays that would be launched into X-ray satellites that would then observe the universe for X-rays. People did the calculations and knew that if you had a black hole and an accretion disk, the disk would get so hot it would emit X-rays. So you train your X-ray telescope in these regions of our galaxy, you create an X-ray catalog. Now, there are other ways you can make X-rays in the universe, but one way you get them for free is in the vicinity of a black hole. So some of the best black hole candidates were first put forth by these satellites, these early X-ray satellites that were tuned to discover black holes in our midst. I'll give the sort of Reader's Digest version of this. There are black holes that are formed at the consequence of the death of stars. And we think we understand the formation of stars well enough to say, well, a star is born with this much mass, and it'll lose a certain amount of mass over its life. All stars lose mass because there's so much pressure and so much energy coming out, it carries particles with it. So they lose mass. The sun is losing mass as we speak. It's called the solar wind. So everybody loses mass out there. The question is, at what rate are you losing mass? Is it a lot compared to your total mass? Is it small? So very high mass stars are not especially stable objects. They remain stars for 100,000, at most 1 million years, and they'll explode and become a supernova. If you're more massive than that, they will not explode because the gravity is so strong that it cannot explode against the strength of the gravity, and it collapses into a black hole. So we expect black holes to have slightly less mass, somewhat less mass than the most massive stars that we know how to make. So if you have 100 times the mass of the sun star, it'll lose half of its mass over its life, and you have a black hole that's 30 times the mass of the sun or 50 times the mass of the sun. Fine. Put a pin in that. In the centers of galaxies, there are supermassive black holes. Hundreds of thousands, millions times the mass of the sun. And they're supermassive, and they're black holes. We call them supermassive black holes because that's how we roll as astrophysicists. All right. Well, could you have black holes somewhere in the middle of these two extremes? We do not know a phenomenon that will give you a black hole that's in between, that will birth a black hole that's in between these two categories. You can make a black hole that eats its way there. Fine. But we don't know how to make one. And we think, my colleagues who've done this, think they've discovered a black hole that is sitting in this sort of netherworld where there's no evidence that it ate to become that massive. And we don't know how to explain it by the formation and death of stars, and is nowhere near the supermassive black hole in the center of the galaxy. So it is the frontier of research at this moment. We're reading the headline now. It's a news digest for science. So black hole shock, theories swirl around the discovery of a physically impossible black hole. So scientists don't use the word impossible unless it's violating a known law of physics. So I bet that was an editor's title. And I don't have a problem. I don't mind a little bit of sensationalism there. You can say it is a black hole that comes from if it comes from an object, it is an object we know nothing about and have yet to discover. We're not going to say it's an impossible object. Every time we point a telescope to the universe, we find something that we never predicted or understood. But let me answer quickly. As you accelerate and as you find yourself in the presence of high sources of gravity, your time actually slows down as viewed by others. Okay, this is part of the relativity of time. And so you basically slow down. And then you come back, you will be younger than your twin sister that you left back here on Earth. And that's just true. We've known that since 1905, that this is the kind of thing that would happen. That, in a way, allows you to travel into the future. But the question is, can you travel into the past? That gets a little risky because suppose you prevent your parents from meeting each other, then how would you be born and then become the person who goes back to prevent them from meeting each other? See, so you get some internal contradictions there. There are people who are working on exotic solutions to Einstein's equations that allow backwards time travel, but they're exotic beyond measure at this point, and not something that is an ordinary consideration. We used to think, not because it was proven, but because it was fun to believe, that you might go through a black hole and come out the other side in another place in the universe. Hawking, a year and a half ago, demonstrated that that's not the case, that all the information that you contain that falls into a black hole actually stays there and later on evaporates out in the form of Hawking radiation. And we can account for all the atoms that went in by the evaporation of the black hole that comes out later. So you didn't go anywhere. You just simply got spaghettified. So no, don't look to black holes as as some hope for your next science fiction story. Yeah, so he's talking about general relativity. Maybe he might remember from the Interstellar film where they went down to a black hole planet and they were deep in a gravitational well. And if you were in an environment of high gravity, time will tick more slowly for you than if you're in a place of low or no gravity. It's relative, okay? So planets, their gravity is not high enough for any of the big planets, little planets, is not high enough for any of this to make any important difference in anybody's life. So don't confuse the fact the black hole was doing the time dilation rather than the planet itself. So if you're just talking about planets orbiting the same star or regular star, this is not something to think about or worry about. We can determine the mass of the black hole by how fast stars are moving at the distance they are from it. So in other words, we're Earth orbiting the sun, and we have a certain speed. We're going about 18 miles per second. I think that's the number, 30 kilometers a second. That's a speed around the sun. That's pretty fast, okay? If the sun had more mass instantly, that speed is not enough to maintain our orbit. and we'll start spiraling in towards it. If the sun had less mass, that speed is too high to be in this orbit. Sorry, it's too fast to maintain this orbit. It'll climb us out to a higher orbit, slow us down, and we'll be in a higher orbit with a slower speed. So in other words, for any object, at any distance, there's only one speed you can maintain and have a stable orbit around it. So when we see stars orbiting something in the center of the galaxy, it is a straightforward Astro 102 equation to calculate how much mass the thing is orbiting. And you get the mass, and you can't see it. It's small. It's a black hole. I thought I might spend a minute offering an understanding of the anatomy of the vicinity of a black hole. So, a couple of things. If you have a black hole and something's going to fall into it, that can happen. But if it's going to fall straight in, it's got to exactly line up with its position in space for it to fall straight in. Most things that are wandering by are not headed straight to the center of the black hole. They're coming off to the side. Well, it'll feel the gravity of the black hole. Its trajectory will be altered. Yes. For it to get to the middle of the black hole, it needs to lose that orbital energy somehow. And thus is the beginnings of what we call an accretion disk. You have a black hole and there's material coming by. The black hole pulls it in and it swirls. And it slowly then feeds the black hole, feeds the monster. As this material slowly loses energy, it gets closer and closer and closer to the black hole, then ultimately gets pulled straight in. Well, all of the material that's coming near a black hole participates in this. Big black holes can have big accretion disks. We're the biggest black holes in the known universe, in the centers of galaxies, where they have a mass equivalent to hundreds of thousands or millions of times the mass of the sun. These are singularly large black holes in the universe, in the centers of galaxies. And we're still debating how they get made. Are they there from the beginning in the formation of the galaxy? Did they occur later? What feeds them? Okay. As long as you're feeding a black hole, it's going to have an accretion disk. And that accretion disk will get hotter and hotter and hotter. Why does it get hotter? Because the orbital energy has to go somewhere. So it goes into heating the gas of this spiraling disk. It gets so hot, it radiates not only in the red or the infrared or not only white hot or blue hot, it is so hot, it radiates X-rays. Oh my gosh, that's highly energetic. Okay, now, how does the energy get out? Which way does it go? It's not going to exit through the accretion disk because the accretion disk is in the way. How's it going to get out? Oh, wait a minute. If it's a disk and I'm energy and I want to get out and I can't get out through the disk, I want to get out above and below. So when we look at the anatomy of black holes, we find accretion disks and plumes of energy spewing forth above and below the black hole itself. And we call these jets. They're jets of matter and energy mixed together. Energy as in photons, very high temperature matter, ejected from the system because it has to get out somehow. There are only two directions left, the North Pole and the South Pole of this accretion disk. So depending on how massive the black hole is, depending how hungry it is, how many stars are getting flayed by the gravitational field of the black hole before they're eaten, all of this combines so that there's a huge range of the intensity of these jets across the universe, galaxy to galaxy. There will always be one that's longer than the others. And just recently in the news, just such an object was reported. More than 100 times the diameter of the Milky Way. Now, of course, it extends as far as you can detect it. At our current detection threshold, it goes 140 times the diameter of the Milky Way. That's out there. So 140 times the diameter of our Milky Way itself is 100,000 light years across. So 140 times that, we're talking way out in intergalactic space. That currently holds the record. We might one day find one that goes even farther. A feature of this object is that it's coming from the center of a galaxy itself 7 billion light years away. That's halfway to the beginning of time in the age of the universe. And by the way, this galaxy has a name. It's called Porphyrion, one of the giants of Greek mythology. It turns out, as you look farther out into space, closer back to the beginning of time, black holes had much more material to eat back then in the centers of their galaxies than they do today. This is the origin of what we call quasars. That's an acronym for quasi-stellar radio source, quasars. Quasi-stellar because a lot of intense energy is coming from a small spot on the sky. It's almost star-like. So we're not as surprised to find such a luminous, extended jet coming from the center of a galaxy that's that far away from us here on Earth. And as time moved on, the black holes ate everything that was near them, and anybody else was at a safe distance, not to be eaten anytime in the near future. So it makes sense that this is an object as far away as it is. The point to be made is there's always one that holds the record. And we've got a new one of late that does just that. So the size of the event horizon, as the black hole shrinks from Hawking radiation, the size of the event horizon shrinks with it. It gets smaller and smaller and smaller and smaller and smaller. And the nature of the radiation that comes out is, you can approximate it by the wavelength of the light that it emits is approximately the same size as the size of the event horizon itself. So big black holes give off radio waves as Hawking radiation. As they get smaller and smaller, they give off higher and higher energy light. So radio waves and microwaves, then infrared, then red, orange, yellow, green, blue, violet, ultraviolet, X-rays, gamma rays. So as the black hole gets littler and littler and littler, the evaporation rate increases, and the nature of the Hawking radiation changes to become higher and higher energy radiation. And then it disappears completely. And in fact, I think the original paper, one of the original papers of Hawking, describes this as a source of gamma rays in the universe that you might observe. Black holes, there's some mathematics derived from Einstein that tells us that inside a black hole, it opens up to another universe, another space-time system. And so if that's the case, what happens to that universe when the black hole evaporates? You can calculate how this will work. It turns out, you might not have known, that as you sit there, as you stand, your feet are closer to the center of the Earth than the top of your head is. Of course, that's obvious. But what we don't carry with us as a general bit of information, is the fact that Earth's gravity is pulling more strongly on your feet for being closer to the center of the Earth than it is pulling on your head. It's not enough to notice, so we don't live with that awareness. But in the vicinity of a black hole, if you do a feet-first dive, it turns out that your feet can be materially closer to the center of the black hole compared with where your head is. In other words, on Earth, if you're 5.5 feet tall, Earth is 8,000 miles across. So that difference it's nothing. But suppose the center of the Earth were like right here, and the distance to the center was, your height was large compared with the distance to the center of the Earth. Then you start feeling this difference in gravity. By the way, that's called the tidal force. And that's what stretches the waters on Earth, okay? That's why you have tidal bulges on the Earth. So that can happen to you. So you're falling down, let's just say it's a feet-first dive. And as you descend, the difference in gravity between your feet and your head begins to grow. And it first kind of feels good. What's the first thing you do when you wake up? Stretch. You want that to happen. Then you realize that the act of stretching is unrelenting. And what begins to take place would be the envy of the Spanish Inquisition. You just continue to stretch, and you can calculate the stretch point where the difference in gravity exceeds the molecular bonds that hold your flesh together. And so there will be a point where your body snaps into two pieces. You will likely break at the base of your spine in that first of your bifurcations. Then those two pieces, as they descend, will feel the same thing your whole body felt a moment earlier. And then they snap into two pieces. So go from 1 to 2 to 4 to 8 to 16. And then you break up into a myriad of pieces as you descend to the center. And that's not even the worst of it. Because what's also happening is the fabric of space and time, as described by general relativity. General relativity, gravity is not so much a force, but the shape of space-time. The shape of space-time funnels you from what was once a wide area down to a narrow area. So that in fact, while you're stretching, you're being extruded through the fabric of space, like toothpaste through a tube. And in fact, the product, there's a word for that. We have a word for how you die falling into a black hole. It's called spaghettification. And so the title chapter of Death by Black Hole, the chapter's called, in there is a chapter called Death by Black Hole. And it's much broader than that because black holes wreak havoc on their environments. They're scary things because they can eat you. And humans tend to be scared of things that can eat them. That's why kids love T-Rex more than they love the Brachiosaurus, which just chews on leaves. T-Rex because it can eat a kid, the way a black hole can eat an adult. So there's a whole section there on ways the universe turns bad. And so so it's an introduction to that not being the only way you can die in the cosmos. So the first wormholes that were imagined were a black hole connecting to its mathematical opposite, a white hole, and you would connect them via a wormhole. So everything goes in the black hole and comes out the white hole. It's mathematical opposite. But then there's more work done on wormholes, especially inspired by Carl Sagan's novel Contact, when he was buds with Kip Thorne. a relativist physicist, astrophysicist at Caltech, where you run through more of the equations and you can, in principle, just punch a wormhole through the fabric of space without reference to a black hole or a white hole. But you need some way to pry open space and keep it there. So you need like negative matter that can pull open space rather than collapse space. And so that works. Our equations give it to you, but we don't know any substance such as negative matter. So wormholes are really just, for now, the realm of science fiction.
So let me start off with just a quick story. I've told this story before, but now it has a place to land perfectly. So some years back, in the early days of Twitter, I was at an airport, and I think it was North Carolina's Charlotte Airport. It's a huge airport, and I had to go from a big plane to a little plane. And I had my luggage. I thought I'd be good and not have to check my luggage, but then I realized now I have to carry the unchecked luggage between two very widely separated points in the airport. So I'm there, and I swear it was like miles. So I get to the gate, and I thought I'd be clever. And so I tweeted, "Can't wait until we have wormholes. In that way, all gates are adjacent to one another." Okay. You just sort of step through a door, everything's connected by. So I thought I was being clever. And then someone cleverer than me replies in my Twitter comment thread, "Dr. Tyson, the day we have wormholes, you won't need airports." Whoa, I just got totally served on that one. So a wormhole, just so people can understand it, if you look at space and time, we've learned ever since Einstein in 1916, when he advanced the general theory of relativity, which is the modern understanding of gravity. We learned that gravity is the curvature of space-time. And what you do is when you are falling towards something, you are simply sliding along the fabric of your space-time towards whatever it was that you're saying is attracting you. And so it's an interesting, it's a different construct from just action at a distance. You're there, I'm here, we have gravity, we pull each other, and that's it. It's a whole other thing going on. And if you think of space and time as fabric, then you can distort the fabric with the force of gravity. So if you ask yourself, can I distort it in interesting ways that might benefit what I want to do in the universe? For example, I can get you around among the planets using the rockets that we've got, and I can get you there before you die. All right? So moving around the solar system takes days to the moon, months to Mars, years to the outer planets, and maybe 1 or 2 decades to Pluto. So what happens is, if you want to visit other stars, then every way we know to get there exceeds the human life expectancy. So you have to find a way to shorten that journey, knowing that the speed of light is not just a good idea, it's the law. There's a speed limit to how fast you can move in that fabric of space and time. The nearest star is 4 light years away. At the speed of light, you watch someone go at the speed of light, it'll take them 4 years. To do that, you say, okay, well, let's just do that then. We're nowhere near the speed of light, all right? This is, so it's hopeless, and that's the nearest star. So you imagine, is there a way maybe you can poke a hole through, or open up a hole in the fabric of space and time in a way that it's curved such that you can take a shortcut from one location to another. So imagine if you had a sheet So compress everything to a sheet, because otherwise it's hard to think of bending 4 dimensions. So our universe is now a sheet. So if I take that sheet, normally I'd have to travel the full length of the sheet to get from A to B, and I want to do that before the TV commercial, okay? And so what do? You warp the space and then open up a hole from one side to the other where the two places are close in this higher dimension. And by doing so, you basically take this portal through, come out the other side, unfold the page, and the no time part is, well, how much did you warp the space in order to do that? And if you warp it a lot, it can happen basically instantly, like walking through a doorway. Or if it's warped a little less, then it'll take you a little longer. But in all cases, your effective speed is way greater than the speed of light, because you basically cheated and went across the other side. It's one thing to have a black hole that all space and time collapses on itself to a singularity, but what you now want is a hole through the fabric of space that remains open. And the configuration of matter and energy to create a hole is unstable against collapse. So in other words, you can have a stable black hole there that's sucking in, distorting the fabric of space and time. But a wormhole requires actively holding it up so that while you're in there, it doesn't collapse on you. Whereas you made one that's stable. See, we got to learn the secret engineering of that. Most understandings of a black hole have you dying if you fall in. If you can pry open a wormhole, because you end up at the singularity, smushed and spaghettified and stretched and broken. But a wormhole, if it's opened and maintained, it could do one of several things. It could be a hole to another part of our own universe. You curved your universe, and you're just going from one location to another. Or you can imagine wormholing out of our universe into another universe. And that way, people in one universe would go through that and show up in another universe. Now the cool part is, if you break the wormhole and collapse it, then you left your universe never to return again. So wormholes are fascinating, and of course they show up in so many different movies, all right? In Bill and Ted's Excellent Adventure, their time-traveling phone booth is basically a wormhole. Oddly, in the movie Back to the Future, they don't appear to be traveling. It is a wormhole, but it's a portal rather than an actual extended wormhole. And one flaw, but I'll give it to them because they did so much else right in Back to the Future, is when they leave the parking lot and end up, this is Back to the Future 1, they leave the park at 88 miles an hour, and they show up in the cornfield, in the farm fields that would become that strip mall. What they didn't factor in is that between those two times, Earth would have moved in its orbit. You can't only travel back in time. You'll also travel back in space if you want to land where you expect to land from where you left. So if he would have time traveled back and landed and in the vacuum of space, and they all would have died, and the movie would have lasted 15 minutes. Your wormhole, if it's going to go anywhere, it's got to go somewhere. Otherwise, it's not only in time, but in space. All right, you want to make sure that it works out that way. So also, is that movie in Time Bandits? That was what's that, from the 80s? That one was the Monty Python crew. So that one was wormholes. In the movie Contact, Jodie Foster basically goes through a wormhole. And so, it's kind of fun cinematically to display one of these, to portray them as you're going through, and it's basically like a tunnel. And in a way, maybe the old TV show Time Tunnel was an earlier concept of a wormhole, although at that time, I don't think we had the term yet for it. By the way, one of the earliest statements about the existence of wormholes was the idea that if a black hole absorbs everything that comes near it, let's take a look at the math surrounding the black hole, and you find out that there are two solutions to that equation that gives you the black hole. One of them absorbs everything, and one emits everything. Okay, so something that emits everything at all times is a time-reversed black hole. So you can ask, where does everything go that enters a black hole? Maybe it's what's coming out on the other side, which we'll call a white hole. How would you connect them? You connect them with a wormhole. So wormholes have very high utility. If you try to think about fun and interesting and useful bendings of the fabrics of space and time. Okay, so the way to think about this is, and this is the way science has worked since basically the year 1600, where Galileo sort of starts codifying what people knew probably should be happening, but no one really did it in large scale. If you have an idea about something, then you test it multiple ways and get other people to test it. And if the tests give you consistent results, you have a new understanding of the universe. When that happens, that knowledge of the universe doesn't go away. It doesn't get undone. What happens typically is you have a deeper understanding of the universe in which that understanding gets embedded. And you realize that you only understood a small part of a larger whole. But the small parts you did understand, where you had multiple experiments that confirmed it, that doesn't change. So the cleanest example of this, and I'll get back to your question, is Newton's laws of motion and gravity. Did anyone see anything move faster than a galloping horse in his day? Probably not. And so the Newton's laws of motion and gravity worked. They worked not only for galloping horses, it worked for the moon in orbit around the Earth, and the Earth in orbit around the sun, and Jupiter's moons in orbit around Jupiter. All right, and for the planets. So, okay, but wait a minute. It doesn't work for Mercury. Mercury's orbit is not following Newton's laws. Is there something wrong with the data? Let's check it. Data's correct. Oh my gosh, what's happening? Einstein comes along and says, I have a new understanding of gravity and a new understanding of motion. And it accounts for this weirdness in Mercury's orbit. Its shape was not exactly what Newton's laws of gravity would give you. Its shape could only be accounted for when you throw in Einstein's theory of general relativity. Why? Because the sun's gravity is so monstrous and Mercury's orbiting close enough to it that it's being influenced by extra phenomenon going on in the universe that's the product of very high and significant gravity. And so then do we throw Newton out the window? No, actually. You know what Newton's laws are? They're what Einstein's laws look like when you put in low speeds and low gravity. If you put in low speeds, they become Newton's laws. In that limit, Newton's laws don't stop working where they used to work. Apollo to the moon used only Newton's laws because Einstein didn't matter at those scales. The moon and Earth and rockets, we're not going fast enough for any of that to matter. But when you start going fast enough, you cannot use Newton's laws. You have to use a deeper understanding. Now, where does Einstein take us? You go into the center of a black hole, you get
black holes from Einstein. Center of black hole is a singularity. All the theories say the matter occupies zero volume, thereby having infinite density. And that's kind of weird. What? No, you can't have infinite. No. That's a limit of Einstein's theory. That's where it breaks down. Some have joked that's where God divides by zero. It's not defined or not allowed. So in Einstein's equations, we're dividing by zero at the singularity. So we all know that as brilliant as Einstein was, and as successful as his general theory of relativity has been, it has limits. And one limit is the center of a black hole, and another limit is the very birth of the universe itself. So we have top people working on trying to resolve this singularity problem. And in so doing, you get to some ideas that, well, maybe our Big Bang, because the Big Bang is not going to go away. All the data support this. So now I've got this Big Bang thing, okay? And, well, is this embedded in something bigger? So when you put like quantum physics and general relativity and you try to come up with some bigger understanding, deeper understanding, string theorists have been all into this, you get a multiverse that came out of the equations. So how old is the multiverse? I don't know. It's definitely older than our universe because it birthed our universe and it births other universes and it births, the way the equations drive it, an infinity of universes. And so that is what comes out of the equations. So that makes the Big Bang a kind of a small part of a much larger whole. And so, yeah, we're ready for that. But the fact that the universe had a beginning 14 billion years ago, and there's the cosmic microwave background, all of these features are intact. They're not going to all of a sudden not apply. That's my point.